Welcome to the final talk of Unit 3. We've covered how to count disease, how to measure associations, how to communicate treatment effects, and how to interpret statistical results. In this talk, we cover two more analytical tools that are essential for reading the veterinary literature and for designing sound epidemiological analyses. First, survival analysis, the family of methods designed for time-to-event outcomes. In veterinary medicine, survival studies are everywhere. Oncology trials measuring time to death or tumor progression, cardiology studies measuring time to congestive heart failure, production medicine studies measuring time to first estrus or days open. Anytime, when did it happen, matters as much as did it happen. Survival analysis is the right tool. Second, standardization, the technique for making rates comparable across populations with different underlying structures. If one herd has a higher pneumonia mortality rate than another, is that because management is worse or because the herd is older? Standardization lets you answer that question. Let's build both. Before we get into the mechanics of survival analysis, let's understand why we need it. The simple approach to analyzing survival data would be to compare the proportion of animals that died in each group. But this approach fails in the presence of two very common features of real studies: unequal follow-up times and censoring. Unequal follow-up is almost universal. In a clinical trial that runs for 2 years, animals enrolled on day 1 are followed longer than animals enrolled in month 18. The animal enrolled late and still alive at trial end has been followed for less time, so comparing raw proportions across groups conflates time at risk with outcome. Censoring is the more nuanced challenge. A censored animal is one whose final outcome, death, relapse, recovery, is unknown. This happens when an animal is lost to follow-up, when an owner withdraws consent, when an animal is sold or euthanized for an unrelated reason, or when the study simply ends before the animal experiences the event. The dog that moves abroad with its owner at week 12 is censored at week 12. We know it was alive through week 12. We don't know what happened after. Censored animals cannot simply be dropped from the analysis. They contributed real time at risk and real information about survival up to their censoring point. Dropping them introduces bias, but they can't be treated as survivors to the end of study either. That would artificially inflate survival estimates. Survival analysis, specifically the Kaplan-Meier estimator and its associated tests, handles censoring correctly by using the time each animal contributed to risk, whether or not it experienced the event. This is why it's the method of choice for any time-to-event outcome in veterinary research. The Kaplan-Meier curve is the standard visual output of survival analysis, and you'll encounter it in virtually every oncology and cardiology paper you read. Let's walk through how to read it correctly. The x-axis is time, days, weeks, months, whatever unit the study uses. The y-axis is the proportion of animals that have not yet experienced the event, survival, progression-free survival, or whatever the outcome is, starting at 1.0, which means 100% event-free at the start. The curve steps down every time an event occurs. A steep, rapid drop early in the curve means events are happening quickly. A gradual, slow drop means animals are surviving longer. The tick marks, small vertical dashes on the curve, represent censored animals. When you see a tick mark, an animal left the risk pool at that time point, still alive, but no longer observed. The most clinically useful number to extract is the median survival time, the time at which the curve crosses the 0.5 line, meaning half the animals have experienced the event and half haven't. If the curve never drops below 0.5, the median survival hasn't been reached, which is actually good news and a survival study. The width of the confidence bands around the curve tell you about precision. Bands are usually narrow early in the study when many animals are still being followed, and wide near the end when only a few remain. Be cautious about conclusions drawn from the tail of a survival curve where confidence bands are wide. The log rank test p-value tells you whether the two curves are statistically significantly different across their entire time course. It's the survival analysis equivalent of a t-test. As always, p-value significance should be paired with consideration of effect size, the magnitude of the difference in median survival times, and clinical meaningfulness. Let's connect survival analysis back to the hazard ratio we introduced in Talk 3.2, now with the full context of what censoring is and how it's handled. The most common type of censoring in veterinary studies is right censoring. An animal is followed for a period of time, then exits the study for a reason unrelated to the outcome. We know it survived to the censoring point. We don't know what happened after. Right censoring is the standard situation when a study ends on a fixed date and some animals are still alive. They're administratively censored at the study end date. The hazard ratio is produced by Cox proportional hazards regression, which is the most common multivariable survival analysis method. Unlike the Kaplan-Meier estimator, which is purely descriptive, Cox regression allows you to adjust for confounders. You can produce a hazard ratio for treatment that controls for age, breed, tumor grade, and any other variables that might confound the relationship. An HR of 0.58 in a cancer treatment trial means treated animals experience the event, progression, or death at 58% the rate of control animals across the study period. That's a 42% reduction in hazard. With a 95% confidence interval of 0.38 to 0.89 and p-value of 0.012, this is a statistically significant and clinically meaningful result. One important assumption to be aware of: the Cox model assumes the hazard ratio is constant over time, the proportional hazards assumption. If treated animals do much better early but then converge with controls later, the hazard ratio changes over time and the Cox model may not be appropriate. Good papers check this assumption. Papers that don't are worth flagging during critical appraisal. Standardization is the technique we use when we want to compare rates between populations that have different underlying structures, different age distributions, different sex ratios, different compositions of high and low risk animals. Without standardization, a comparison of crude rates between structurally different populations can be deeply misleading. Our dairy herd example illustrates this perfectly. Herd A has a 4% annual pneumonia mortality rate. Herd B has a 2% rate. Naively, you might conclude that herd A is being managed more poorly, but herd A's population is predominantly older animals who have higher pneumonia mortality regardless of management. Herd B is mostly young stock who are more resilient. The difference in crude rates may be entirely explained by the age structure of the two herds, not by any management difference. Direct standardization. You apply the age-specific rates from each herd to a common reference population, a standard population with a defined age structure. This produces age-standardized rates for each herd that represent what the mortality rate would be if both herds had the same age structure. Now you can compare them directly. Indirect standardization. You take the age-specific rates from a reference population, national average rates, for example, and apply them to your herd's actual age structure. This produces the number of deaths you'd expect if your herd experienced national average rates. You then compare observed deaths to expected deaths. The ratio of observed to expected is the standardized mortality ratio, SMR. An SMR greater than 1 means your herd has higher mortality than expected after accounting for its age structure. Less than 1 means lower than expected. Let's work through a direct standardization calculation to make this concrete. We'll use the 2 dairy herds and we'll standardize to a reference population of 1,000 animals, half young, half old. For each age group, we apply each herd's age-specific mortality rate to the standard population. Young animals, standard population has 500. Herd A's pneumonia mortality rate in young animals is 1%. Expected deaths in the standard young population at herd A's rate 500 times 1% equals 5. Herd B's rate in young animals is 1.5%. Expected deaths 500 times 1.5 equals 7.5. Old animals. Standard population has 500. Herd A's mortality rate in old animals is 6%. Expected deaths 500 times 6% equals 30. Herd B's rate in old animals is 5%. Expected deaths 500 times 5% equals 25. Total expected deaths in the standard population, herd A gets 5 plus 30 equals 35. Herd B gets 7.5 plus 25 equals 32.5. Age standardized mortality rates, herd A 35 divided by 1,000 equals 3.5%. Herd B 32.5 divided by 1,000 equals 3.25%. Compare these standardized rates to the crude rates. Herd A was 4% crude and 3.5% standardized. Herd B was 2% crude and 3.25% standardized. After removing the confounding effect of age structure, the rates are nearly equal. 3.5% versus 3.25%. The apparent doubling of mortality in herd A was almost entirely explained by its older age structure, not by worse management. This is standardization doing its job. The practical lesson: whenever you compare rates between populations with different structures, whether different herds, different regions, different time periods, or different study populations, ask whether the comparison has been standardized. An unstandardized comparison of structurally different populations is potentially meaningless. The method to use depends on the data you have and the question you're asking. Direct standardization requires that you have reliable age-specific rates for each population you're comparing. If you have those rates, direct standardization lets you produce comparable age-standardized rates for all groups simultaneously. This is the method of choice for comparing multiple populations, multiple herds, multiple regions, multiple time periods on the same footing. Indirect standardization and the SMR are more practical when you only have total counts, not age-specific rates, or when the numbers within age groups are too small to produce stable rates. You take the standard rates from a reference population and apply them to your population's age structure to produce expected deaths. Then you compare observed to expected. An SMR of 1.3 means 30% more deaths than expected based on the industry benchmark after accounting for your herd's age structure. In veterinary practice, indirect standardization is probably more common because most practitioners and epidemiologists are asking, how does our herd compare to the regional or national benchmark, rather than how do multiple herds compare to each other? The SMR provides a clean, interpretable answer to the first question. One important caution about the SMR: SMRs from different populations calculated using different reference populations are not directly comparable to each other. If you've calculated an SMR for herd A using one national benchmark and an SMR for herd B using a different regional benchmark, you can't compare those SMRs. This is a common mistake in the literature. Direct standardization is the appropriate method when you need to compare multiple groups simultaneously. Here's a summary. Survival analysis is the right tool when timing matters, when you need to know not just whether an event happened, but when. Censoring is the key methodological challenge. Animals whose final outcome is unknown but who contributed time at risk. The Kaplan-Meier curve visualizes survival over time. Read median survival from where the curve crosses 0.5 and treat the tail with caution. The hazard ratio from Cox regression compares event rates between groups, adjusted for confounders, with HR below 1 being beneficial. Standardization removes population structure as a confounding factor in rate comparisons. Direct standardization produces comparable rates, indirect standardization produces the SMR, and an unstandardized comparison of structurally different populations may be telling you more about demographics than about the question you're actually asking. That completes Unit 3. All 11 concepts are covered. In Unit 4, we move to causation, bias, and confounding, why correlation is not causation, how studies go wrong systematically, and what confounding is and how to deal with it.